thought he was ready.
It's probably worth it to like start streaming already in like the meetup phase thing, get the rings up even before we show up here.
Formula.
Yeah.
Formula. Where'd it go?
Oh no!
Okay, so I understand that even
typically work with
like, I can
K8S
see
or
where that's sure, that's
Okay,
right?
fine.
But like, then you get to the
Oh, okay, we're ready.
Then,
like, how did you figure out to break it down like
I mean, is the stream supposed to be up?
The YouTube, is it on Twitch? Which one?
It's both.
I don't see it yet.
It's on YouTube online. It's online on YouTube.
Okay.
But Twitch?
It's streaming on YouTube.
Is Twitch not up? It should be going right now on Twitch.
I see it on
I see it
Twitch.
on-
It is streaming on Twitch. Yes. It says live. One viewer.
It's on YouTube now.
Basically always just like
Uh,
config and then the
All right. Thank you for the patience. We got the technical difficulties. And as a reminder, please stay off the stage. And if you want to have a side conversation, go in the far back corners. Also, as a reminder, we are recording the lecture. So be aware we now are streaming on YouTube and Twitch. So thank you. Sofi, please take it away. This is just a prop if you're on the stage.
Thank you. Well, I will start with a small presentation. I'm Sofi. I am telecommunication engineer. I'm working on satellite industry right now, and I will talk about a little bit on how we verify our designs. Probably when you want to do something very complex, you probably will need to create some kind of chip or electronic design to do that. If you need a really high speed processing, probably you will use an FPGA or an ASIC to do that. And the problem there is it's really hard to debugging this electronics design in real life because there is a problem. You need an oscilloscope or something complex to do that. And you want or you can catch up a lot of functional problems before create this in the reality. For that, in the industry, is usually to use simulation. And today we will talk on how you can do that simulation and which problem you have to do that. Today we will talk. You have an standard which is UVM, which is the center topic of this presentation. Let's talk about this a little bit. On the end of the presentation, we'll talk a little about the problem I am working right now, and which you can do with not using exactly UVM. UVM is created by Acelera System Initiative, which is a non-profit organization, which was founded for these big players. With we say you can see here AMD, Exilium, ST, Synopsys, AMD, Intel, Siemens. How you see here the big player for the chips and for the simulators. Cadence, Synopsys are the owner of the simulator to allow you to simulate the RTL. The RTL is how you describe this logic you want to implement. Here you can implement anything, but in my world, usually you will implementing data processing. For example, filters, correlators, or this kind of things, estimators. Now, in this company is implementing or launching a lot of AI designs to be easier to be implemented here, but it's almost the same. The idea is you have a problem to processing a lot of data be really fast, and you will using FPGA or will be developing an ASIC chip. Even if you are developing a chip, probably you will use a FPGA to do the proof of concept of the design. And well, how you say, the idea here is how to do the verification of that design. And all these people in some point put his effort in creating a standard for that, and that standard is UVM. Here we can see a timeline. In the start of the century, this standard doesn't exist. Each big, these are the big players of the simulators, Synopsys, Cadence, and Mentor Graphics of Siemens. In the principle of the century, anyone do anything different. And it's really hard to jump from one simulator to another one because the language was different. In some point they found it is not the best they can do. And in 2010 they decide to put all the things they were developing before in only one statement and only one standard, and the 3 simulators today use the same standard to do the simulation. These have really good acceptation in the market because today you can jump between the simulator. It's not free because I have to do the migration from Siemens to Cadence. It's not plug and play, but it's pretty easier today to change the provider of your simulation licenses. I don't know if someone developed RTL here, but you have 2 languages to describe these logics, which is Verilog and the other one is VHDL. It was possible because they developed the SystemVerilog. The SystemVerilog is an extension of the Verilog language, which include all the things you need to describe this environment to make the simulation and the verification. I will go deeper into that. Here is a little history about the standard, and you see it's really alive today because the last version is for the last year, the August of the 24. It is open. You can download this from the Accelera website and use this forever you want. The problem is not the standard or the libraries. The problem is the license of the simulator, basically. Why these big players do this? Basically because they want to improve and make this effort to do the verification more reusable for the next project. They found they're investing a lot of time in verify a chip or FPGA design, and they want to reuse a lot of that code in another projects. And that is what the core pros of this standard. For that, they are thinking about reliability, standardization, scalability, and automatization. The idea here is to reduce the cost to make this verification and make this verification faster than you have to develop your own test bench schema. Which is the problem with this standard? The head is a mess to try to learn about this. The step learning curve is a problem. Probably is overhead and complexity. If you are trying to verify a small design or something really small, maybe this can be too hard to implement a test bench developed with UVM. If you are using SystemVerilog and you are using the UVM libraries developed by Accelera, probably you will need to pay for the licenses of the simulators. And that is not good. We don't want to do that. And the second problem here is the performance. If your test bench have a lot of randomization or a lot of coverage, we will go over deeper on that. Probably will take a lot of resources to do the simulation. I say SystemVerilog UVM can be very complex. Here are some numbers. For example, today UVM have 355 classes, 1,000 methods. It's huge. This standard is very, very big. How is the mix between how Cadence do the things, how Siemens do the things, how Synopsys do the things? There is a lot of way to do the same, and even the UVM with going with new version, you have the old ways and the new ways to do the same. For that reason, it's a little mess to try to understand this standard. That is exactly what I do in my work, try to understand this and use it. The other hand, or in the other way, because can be a little complex to do or to use, is because it is this part of the SystemVerilog which is new, is object-oriented programming, and usually these standards and this language is used by designer, by electronics, who are not software engineers, and probably they are not so confident using the properties of the object-oriented programming, like herency or polyformism. That is the true reason, because it's very complex to use this, but it's even the best solution for now. Here are some comparisons. The good thing of SystemVerilog is not only for UVM, it's also for SystemVerilog. You can constrain your randoms. The idea here is a little bit to produce random inputs to the design, and in that way you can see and try to find the bugs randomly and running a lot of seeds of these random inputs. For that you need to include constraint, which is make this randomization in proper values of the design input. And SystemVerilog is a really nice language to do that. Could be a little complex to learn, but they have all a part of the language dedicated to modify this distribution of the random input. It's also easy to define cover groups and cover points. The cover groups and cover point is the way you can create a histogram. When you are running your simulations, you will recovering data for the places you are going through the design, and then with the data you can understand if you go over or not in that part of the design. It's important to know how good is your test, or how good is your test bench to record to go to all the parts of the design. The problems: SystemVerilog is also a complex language, because with SystemVerilog you can describe the electronics, you can do the simulation, and you can do all the test bench and checkers. If you see, the SystemVerilog have 221 keywords, and if you compare this language with C++ or Python, it's really a really big language. The other problem, how we said before, if you are using UVM today, you have to use a proprietary simulator. There is some initiative to do this with open source simulator like Verilator, but today is only supporting the UVM implementation in C and not in SystemVerilog. That is the reason, because today this big player is still taking almost all the market. How we say, there is another options to implement UVM which are not in SystemVerilog. You have implementation of the UVM libraries in Python, which with CocoDB allow you to make the simulation with all open source open source initiative. I do that. I work with that. The problem is if you are using some, if some part of your design are intellectual properties and you have this design encrypted by one of these vendors, you don't have the keys to simulate this with CocoaDB and PyUVM. If you are stimulating your own electronic design and all the code is yours, you can use this, but usually in the industry, probably if you are using an FPGA, probably you will be using some IPs from the owner of the FPGA, and you are not able to do the simulation with this open source option. You also can find all versions or all implementation of UVM, which is used to create the actual version. And you also can found in the internet the implementation of UVM with the System C. The good thing to use the System C version is you can incorporate models. If you have your own models of your design in C or C++, it's much easier to integrate that to your test bench or your simulation with System C. Here, it is not so technical, but I want to share some numbers because for someone is interested in maybe the commercial part. These numbers are from Siemens. It is a report they made, and it is the resource strength in the ASIC industry. Here we can see the comparison between the design numbers of the engineers and the verification engineers, and how in the last year is how increased the number of verification engineer the market is requiring. If anyone is interested in working in the ASIC industry, maybe be a verification engineer is a good idea because it is a trend which is persist on time. Here's almost the same, but here the projects are not implemented in ASIC, are implemented in FPGA. Here the number of verification engineers is not exactly the same like design engineers. The reason of this is because the nature of the FPGA designs, because here you can reconfigure the board and you have more access to the internal signals in FPGA than ASIC, and maybe you are available to do more debugging in lab, and not with that you can compensate, don't have a really good or very expensive test bench. And here we are seeing which is the market using to make the test bench. How we see, almost the market in ASIC is using the Acelera UVM standard, which is what we are talking about here, and some part of the market is still using the before efforts of the Mentor and Synopsys verification options, and a really few part of the market is or not using anything, which is really strange, or using the CocoaDB option, which is the open source option. And here is the same, but with the FPGA project. How we say, is still the leader in the market, the Acelera UVM implementation. But you can see the proportion of the market which is not using anything is a little bigger. It's because the FPGA probably don't require to have a really strong verification. The reason because the ASIC require a strong verification is because do the type out and send the design to be implemented in Silicium is very expensive and very long process. probably you have to send this to some foundry in China, and that is not easy, and that is not cheap. That is the reason why the ASIC industry is more careful with the design which they implement. And then let's talk about a little bit about UVM. The UVM basically is a test bench, but in a simulator. You will have a DUT, which is a device under test. In this example is an SPI with IPv interface, which is protocols of the access register to the design, but doesn't matter, could be anything. You will have a test, and inside that test probably you will have an environment. You can think in the environment like a table, and you will put things over the table. In that table you probably will have agents. The agent will be the responsible to drive and monitoring the signal to the DUT. You can think this like oscilloscope with a signal generator, if you are familiar with a lab. After that you have a configuration class. Then the configuration class is like any configuration class you have in any software. The idea is you can control the behavior of this component through that. And the most important part in here is you will have a scoreboard. And the scoreboard is the more complex part to develop, because the scoreboard have to predict the output transaction of the design and compare the output transaction which are monitoring for one of the agents with the predicted, and see if a match or no match with that. Maybe implement the scoreboard could be hard, because you have to re-implement all the logic you have in your DUT in this scoreboard. But today you can, if you have your prediction or your model implemented in Python or MATLAB, you can call this prediction through SystemVerilog and reduce the time which is required to develop the scoreboarding. But it is a typical architecture of the test bench implemented with UVM. Here, for the people who are more familiar with object-oriented programming, it is the tree of the hierarchy of the classes. How you see is not too big. Probably you only will use the classes in yellow. But SystemVerilog is one linear oriented object programming. That means any class only can have one father, and for that reason it's very linear and very easy to follow the hierarchy here. There is two big kind of things inside that bench. One are the UVM transactions, a item or sequence, which are objects will be live in some part of the simulation, will be created and destroyed in all the simulation all the time. And you will have components which can be a monitor or agent or subscriber, which will be alive in all the simulation time. That is the big difference with these two. And the good thing to use the standard is all the relationship and all the input-output between the different components are developed and is unmasked under this standard. You don't have to be a problem to connect a subscriber with another one, because in the end FIFO and this connection is solved by the standard. Here this slide is because I want to talk a little bit about the scalability. One of the good things to use this standard is you can scale really easy the test bench. And here we can see we are including two different environments inside one bigger. And that is what the standard is referred when it's talking about scalability. You can reuse your block level simulation in a top level simulation, and you can reuse your environment, and you can configure using the configuration class. You can make this agent be passive or active. Basically, the difference is if your agent is passive, it will be only monitoring the signal like a oscilloscope. And if it is active, will be injecting signal and monitoring signals like an oscilloscope plus a signal generator. In that way, you can create your environments with the correct configuration classes, and you can turn on, turn off your agent, and you can inject or not signal to the UET, and you can do that using the same classes definition you have for the block level simulation. That is the good thing of this standard, and I think it's the principal reason because it is used and taken for almost all the market in design RTL. Well, here is a list of the principal topics of the standard. Some of them already talking about how we say we have object will be alive sometimes and will be created and destroyed in the simulation. You have the component will be alive in all the simulation lifetime. You have the TLM, which is the port which are connected between different components. The macros is a way you can change your code in compilation time, depending if you define or not some keywords. The event or the event pools is a way you can synchronize different parts of your test bench, and is pretty similar to callbacks, which is pretty usual in software. You can synchronize your test bench. You can define an event if something happened, and another thing will be triggering waiting that event. The phases is a really UVM concept. I don't see that in another part. The idea here is you can take your simulation time and break in small pieces, and you will put that name. For example, I know the reset phase, the start phase, the run phase, and the end phase, or whatever. And you can control what will happen in each part of these phases. Transaction, which are object. The sequence is the way the input are created. The sequence is controlling the input in the agents. The virtual sequencing is the way you have to control more than one sequence at a time, because if you have different agents, you will need control. I know for one interface you can driving register access, for another the data path, and you need to control all these things in parallel. For that reason, you have virtual sequences. Callbacks, how we say, is the same in any place. The coverage, which I already talked about it, is the way you have to know if your test bench is going to all the part of your design or not. And you have the configuration, and the factory is the way you have to propagate the handlers to different components in all your test bench. The layering and the register model is a really, advanced topic, because it is the way if you are, suppose you are debugging an Ethernet interface. How you know the Ethernet have different layers. You can have the TCP/IP, and after that, the Ethernet itself, and in the end, the physical layer. Well, you can create a component for one of them of this layer of the model, and you can have the information translated for each one of these layers. It's really useful when you are debugging a communication protocol. In the same way, the register model is an application of layering, and it is related to access to registers and memories. If anyone have any experience with that, you know this could be a little mess to have this mapping between addresses and values, and this register model allow you to handle this in an abstraction way. How we say, he was a very schematic way to do an scoreboard. How we say, you need to make the prediction for one place and then make the comparison. If you are doing DSP processing, like a filter or like a correlator or whatever, or an EI model, whatever, probably you will really have this implemented in some simulation option like Python with NumPy or C or MATLAB, and you can integrate that model in your RTL and electronic verification. The way to do that is could be a DAPI or a system call. This is my expertise because it's in the project I am working right now. We have a lot of prediction made in MATLAB because the algorithm team is working in this software, and we need to compare it if the design implemented in the hardware do the same these models do in MATLAB. Here is an example of layering. How we say it is a component. The idea here, you have this component connected to an agent. The idea basically is you will have your monitor, is like your oscilloscope, will be monitoring the signal of the DUT, and you will translate in this signal to another interpretation of the same information. And this allows you to increase the abstraction of the test bench. And in the other way, you have the sequencers will be translating the high-level instruction in low-level instruction. It is really, really useful. And it's important to have this idea if you want to make a really reusable test bench and you want to really reuse this in another project. You have to take your time to think about the abstraction level of your view design. How we say, here we have example of the register abstraction layer. If you're working software or anything, you want to handle the configuration of a chip or anything, you have this problem to handle all the addresses to configure the I'm thinking maybe a Steam micro or whatever. The idea here is don't have to handle with the addresses in the test bench. If in the other way you handle with the naming of the register, because the addressing could change. No, you can use this to don't have to think about the addresses for one place. And the other thing which is really good to use this kind of layer is don't think about the physical interface, because probably in some kind of duty you can have an SPI accessing, in other one you can have access for full accessing, in another one, or in the same you can have, a serial accessing. If you are using this kind of thing, you can connect these interfaces to the abstraction layer, and you can forget of the low-level signaling process, because you are do a bright, and this is in charge to make the translation between the bright sentences and all the same signal you have to send to the duty to make a write to a register or to a memory. Well, it is a little bit about which is the market today with this kind of things. UVM is UVM give you a way to do the things in a very repetitive way. You always have a test, you always have an environment, you always have an agent. You don't have a lot of things to think about the architecture, and that make for that reason there is a lot of effort in the market to create frameworks. In this framework, you give the skeleton of your test bench and give you the first input of the code you will use to create this test bench. The most useful open UVM framework from Siemens is really used. For my test is a very complex. I prefer to have an option to have a test bench with not so many components like Siemens proposal. And for that reason, in the company I work, we developed our own code generator with own framework. And for that, we are using PyYAML and Jinja. If there is someone from software, probably will be familiar with these two. And with that, we have a YAML like input. We want to say, well, I will have an environment with this component and with this agent, and give us the first try of all the files and all the description in a generic, the generic part of the code to create that. And for us was very useful. Most of all for the junior engineer, because this output give you also the to-dos, very clear to say, well, here you have to implement this. That make us very, allow us to have juniors working faster than in a place than before we have these tools. And here's the fun part, or my favorite part of the presentation. I will talk about how a test bench work, or how right now we are using a test bench. You have some years ago, the cool way to do the things was with directed test. There you have a test to, I don't know, you have a memory, you have a test to verify the writing, and you have another test to verify the reading, and you have a test for each feature of your design. The problem of that is not the best way to find the bugs, and probably will be difficult to find bugs when you are doing mixing inputs. The second, what come in to be useful after that is the constraint random. Here the idea is, okay, I don't will thinking about a sequence. I will put random inputs. I don't know. I will randomize between writing and reading. I will left the random way to do the things. I know. I will randomize. I will do the writing one time and the reading with some distribution, and will left the random go through the design easily. And all the statistical studies prove that is an efficient way to find the bugs than the directed test. Here is abstraction way to think about the design. You can think about the design like a space state, and here you have the reset state, which is the first state when you started always, and after you can record, or you can go through this state with some way. And when you are running a random constraint test, you are recording this space with some distribution. You will go through some golden threads. Which is the problem here? The much problem here is how you know you run enough times your test bench, your simulation. How you know you go to all the state interesting or important of your state space. For that, you need to do coverage. Then the constraint random always go to the hand to the coverage. And the coverage is the way to know how good are your test bench to go through this space state. I have only one disclosure here is, if for some reason you need a directed test, you can create that directed test, putting more constraint in your random test. You are not missing anything here. For some reason, it's typical in my work. I know. You send the FPGA design to the lab, and in the lab it's not working, and you want to replicate in the simulation exactly the same configuration they are doing in the lab. You can do that, including new constraint to your random test bench. Here is the flow of all the simulation. You will have a list of seeds, you will recovering, and you will running, and you will have in some point some coverage, which will be creating this histogram through the design to say, well, I pass for here, for here, for here, for here. You will have the scoreboarding seeing in each of the simulation if the output is we expect is the expected output. It is the flow to do a simulation and do a coverage and do a test bench for a RTL design. Doing for FPGA and doing for ASICs. The idea here is you have to develop a lot of time in your random sequence. You have to develop a lot of time in your scoreboarding, but after that, the only thing you have to do is run a lot of seeds of this random and see if your coverage will go to an acceptable number. But the problem here is, your coverage maybe will take a lot of time to recover all the space. Or maybe your test bench is not good enough to go to all the possible states of your design. It is really new. It's a new feature. It is not UVM. It is another complete different things. The idea here is you will have a mathematical expression of your new design, and will we recover all the space, all the state space, doing some assumption and putting some rules. And the idea here is you will record all the space which is allowed by your assumption, and you will be checking every time if your restriction is respected or is matched. Which is the problem here? It looks like really nice because you can forget for the coverage here, and you can forget for the randomization because you are going through all the state possibles. The problem here is maybe all the state space is too big, because I know, think about a data pad with you have 64 bits of the representation. That is all the possibilities of this value combined with all the possibilities of the multiplexer or whatever is a huge space, state space. It will end, but maybe it will take some years to make this simulation. This is called formal verification, and is a really fancy thing which is coming now in this industry. But the problem, the principal problem here is that state space could be really big. I take some courses about this, and the solution for that is cut off your design in smaller pieces and try to use these techniques in a small pieces of your design. I want to introduce this here to say, well, there is another things that just random input and coverage and scoreboarding, but today is not the most used in the market yet because we have this limitation. That is the principal content of the lecture. Right now I want to talk a little about how we use it or where we use it. Right now I'm working in a company which is called IST Mobile. They are doing satellite for 5G telecommunication. The idea is give 5G cell phone broadcast or whatever to any kind of the mobile device with satellites in any place of the earth. For that, the satellite have a really big array of antennas, and after that antenna, you have to process in the data to do the beamforming. And my team is working in verify and develop this signal processing to can appoint and work with the beamforming of all the antennas array. I don't know if there is any question or if someone want to ask something. I don't know how. Okay, thank you, Vitex.
So for the Q&A session, this is the microphone. If you're grabbing the microphone, your voice will be amplified. Any questions?
Here.
And I guess I can mention that people on streams can also ask questions.
Thank you. So if I understood properly, UVM is for kind of virtually emulating new chips that are not yet manufactured.
Exactly. Right? Yeah, exactly. In the first stage of your design, you will have a description of your chip and what you expect your chip doing, and you have the specification, what you want to do with that chip. And the idea is using UVM, you can simulate this chip, make this comparison between the specification and the output of the simulation, and see if your design or your chip is doing exactly what you expect to do. The idea to do that in simulation is because it's easier to find a problem in the simulator than do that in the real life when you already have the silicon doped and connected and yeah, that exactly is the idea.
Okay, thank you very much.
You're welcome.
If anyone else wants to ask a question, here is a microphone.
Hi.
Yeah, let me take the mic. Oh. Thank you. So, I'm in a bit of a different field. Like, to be honest, I'm working computer science, and it's kind of funny how the idea of when you work in programming, you have a similar idea. If you write some code, and inevitably you need to write the test for the code you specifically write. So you got to make sure that everything runs properly. Kind of a similar idea that you have here. But specifically in programming, you effectively have the same developer to make the code itself and writing the tests. How did it end up in like in your area of FPGAs and ASICs, that the ones designing the FPGAs and ASICs and the ones testing and doing these specific tests end up being choose separate jobs? Is it just that how historically it ended up, or is there anything more to it? And that's it.
Okay. For the reason, the idea here is have an independent verification, because the idea is both the verification engineer and the design engineer will be start with the specification, and one will be developing the test bench and the other one will be developing the design. The idea is increase the confidence the test bench give you, because if the same person make both, if that person is misunderstanding the specification, will do the same missing interpretation in the design and in the test bench. And these industries invest a lot in verification and make an independent way in verification, because the problem is because the economic equation give you that answer is that effort is good enough to invest, to have two different engineers looking for the same specification. That is way.
Thank you.
Great. If you're just an example, but for example, in a previous project I work, we are the independent verification team for a nuclear design, which is a FPGA, which is replicated in three different FPGA, and it's controlling when the bar will control the power of the nuclear facility go down or up. And in that case, it's even more important to have an independent verification, because it's delicate problem. And for example, one of the things we are working in the past is in do a external and independent verification for nuclear designs.
Okay, we have one question from our Discord chat.
Great.
Can UVM Suite do tests in real hardware, or is it only for simulators? Can it do end-to-end test the device as black box?
Yeah. You are in. I will answer first the second question after the first one. There is any techniques to do this. You can take the design like a black box and you only saw the input and the output, and that is the way to do an independent verification. And that is when we work in project like the nuclear, or we are like a consultant, external consultant, we do that. We think about the duty like a black box, and we really don't care how it's implemented inside. We have our specification and go to the output and see if the correct output. But if you are working like a verification engineer and in a develop process, like is right now my case, probably you know how the RTL is implemented, and probably you will give to the designer some debugging features. It's not 100% verification job, but you have all the tools to make easier to find problems or to solve problems to the design. And then you are using a gray box architecture, because maybe you are seeing some signals inside the design. for example, right now I'm working in a startup in satellite industry. We want to do really fast design to be shampoo to space faster, basically. And then you still have this problem. You will start to see inside the design, and you try to make the design work and the lab work easier. And that impact on how you do your verification or your test bench. That is the second part. And the first one, yes, you have all the information to put the ramp up of the design working in your simulation. You can create this sequence of software using the simulation sequences, and with that, I, for example, go to the lab and use it for the test in lab. You can do that. That is possible, and it's very useful because you have exactly all the accessing to put the design in the correct place to work correctly, basically. That is the idea. If not any more question, I want to say thank you for your attention, for your time, for Apotec to invite to me, and for Vitex to all the team to be here. Well, that is all from my side.
Amazing, excellent.
Clap, clap, clap. Thank you, guys.
Thank you so much, Sofi, for the wonderful lecture. That seemed pretty enlightening, and we had a lot of people watching on the streams. So we've had our Twitch, YouTube, and Discord going. For anyone who's still watching, this is DGen Tech. We have these as a monthly lecture. We're a group of working professionals in the science, technology, engineering, mathematics, and medical fields, so STEM fields. And thank you very much, Sofi, for giving that lecture. That was I really like these more technical topics. I think a lot of people here come for this sort of stuff. So we have our next meetup later, and for now, this meetup is the official part of this meetup is now concluding. So we will be sticking around. We may transfer over to a better world with a bit better lighting. This is a great lecture world, not so great of a hangout world. But please stick around and talk to people. And if Sofi's around, I'm sure you can go talk to her directly. So once again, thank you everyone for giving us your time, and thanks for checking out DGen Tech.
Thank you.
Oh, and Apotec, any last announcements? Anything you can? Yeah. Yep. Yeah, we're going to cut the streams now. All right. Thank you, everyone.